Hello, we are continuing our methods of integration today by looking at some trigonometric functions. Previously, we've seen how to integrate sine and cos and sec squared because they're our usual functions. We can integrate those just using the derivatives. In today's video, we're going to have a look at more complex things, integrals like tan squared or this monstrosity. We'll see loads of different methods. A lot of them involve identities, so I'll go over all the identities that you need to know. But some of them also involve a few tricks, which is worth picking up along the way. The first two formulas that are worth remembering are the double angle formulas. And I say two, but it's really four, because the cos 2x formula has three different versions. When we're doing identities in integration, these two are probably more helpful, but you might see the top one used as well. The third and fourth identity that you should know comes from the fact that sine squared plus cos squared is equal to 1. If we divide both sides by sine squared divided by sine squared is 1, cos squared divided by sine squared is cot squared, and 1 divided by sine squared is cosec squared. Similarly, if we divide both sides by cos squared, sine squared divided by cos squared is tan squared, cos squared divided by cos squared is 1, and 1 divided by cos squared is sec squared. So these two formulas are quite useful if we ever need to integrate, for example, tan squared, because we can write it in terms of an integral that we know. As well as their identities, you'll also need to know the derivatives of the inverses of the trig functions. So this one is 1 over square root 1 minus x squared. This one is very similar, but the minus version. And this one is 1 over 1 plus x squared. These would be the most helpful if we have to integrate the inverse of the trig functions. With the formulas out of the way, let's get cracking with some examples. Let's integrate tan squared x. Thinking through the formulas that we just saw, we're going to want to be using the formula tan squared x plus 1 is equal to sec squared x. And the reason is, sec squared was one of the integrals that we know. If we rewrite this, tan squared is sec squared x minus 1. And the integral of sec squared is tan, because the derivative of tan is sec squared. Then we minus x, and we plus c. Not too bad. If we wanted to integrate sine squared, the process is a bit more involved. The only formula that we saw that had sine squared in, other than sine squared plus cos squared equals 1, was cos 2x is equal to 1 minus 2 sine squared x. And in fact, it needs to be a thought process, an immediate thought process. When you see sine squared or cos squared, you want to integrate it, double angle formula is the way to go. The reason is, if we can rearrange this, I'm going to add 2 sine squared x on both sides. And then I'm going to divide both sides by 2. Like this. Can you see that this is now nicely integrable? Something that we've seen before at least. So the integral of sine squared will be the integral as 1/2 minus 1/2 cos 2x. The integral of a half is half x, and the integral of cos 2x is 1/4. So a half times by a half from this 2, and then it changes to sine 2x plus c. Now as a test, try and integrate cos squared x by using another version of the cos 2x formula, this one in fact. If you integrate this and then add the two answers together, like this, you should get x, because sine squared plus cos squared is 1. So this answer should be x. So just make sure if you add the integral of sine squared and the integral of cos squared, you do indeed get x. That's just a nice little check to see if it works, but really it's the double angle formula that you need to associate with the square of sine or the square of cos, and how to integrate them. What if we wanted to integrate sine x times by cos squared x? This one looks a bit more complicated, because it is. The way that we're going to tackle this one is by a substitution. If you're not as familiar with the substitution, check out my video on it. You should get, in the end, after some working, minus cos cubed x divided by 3 plus c. And if you're using the reverse chain rule, you should get the same answer too. In fact, this will work for any power of cos. Doesn't matter the power, because the substitution that you make will always cancel out with this when you find dx in terms of du. And similarly, it's cos x sine to a power. Give you the same result, but this time the substitution that you have to make will be u is equal to sine of x instead. If you've got sine or cos to an odd power like 3, and then you've got the other function to any power, I'll just call it n, you can use that same substitution, u is equal to cos of x, whatever is to the bigger power. The reason why this works is it will cancel out one of the sines and it will leave you with sine squared, but the sine squared can be written as 1 minus cos squared, which is 1 minus u squared. Again, check out that video on substitution if you're not familiar with it. If you wanted to integrate sine cube x, then we could use the triple angle formula. You could derive it, rearrange it, and then integrate it. But there is a nicer trick. If you can rewrite this as sine x times by sine squared x, okay, it feels like we've not done much. But then we can turn this into sine x times by 1 minus cos squared x. And this is really quite helpful for us. If we expand these brackets, this would be sine x minus sine x cos squared x. The integral of sine is minus cos. And then this second part of the integral will be 1/3 cos cubed x, like we saw before, and then plus c. The same idea will work for cos cubed of x. Try it out and see what you get. If you see something like this, where the coses and the sines have the same power, or sine squared x, cos squared x, for example, the idea that you want to use is the double angle formula for sine. The one on the left is a bit more obvious. If there were 2 at the front, it would be exactly the formula. So this is a half of sine 2x. And then this one you can integrate using the rule. There's a 2 in the middle, so we divide by the 2. And then the integral of sine is minus cos, like this. For the one on the right, you want to use the same kind of idea. We'd have to rewrite this as 4 1/4 on the outside, because then we can write it as 2 sine x cos x all squared. So I've added a 4 because then this 2, when we square it, will become 4, and then it will cancel out. This then becomes, well, 2 sine x cos x is sine 2x, and that's squared. But we know how to integrate sine squared now. We have to use the double angle formula. So to spell it out, this is the formula that we need to know for the double angles. And if we rearrange this, we get, which means that, but what's in our integral? It says 2x. So what we need to do is we need to times what's in the brackets by 2. So we will get sine squared times by 2, 2x, is a half minus a half cos times it by 2, 4x. And then we can go ahead and integrate these. We will get 1/4, the integral of 1/2 minus 1/2 cos 4x dx, which will be, this half will integrate to a half x, times it by 1/4 will be an 8x, This will integrate to minus 1 over 8 sine 4x, which will then be minus 1 over 32 sine 4x, and then plus c to finish us off. So if you ever see a sine and a cos to the same power, you probably want to use the sine double angle formula. You may then need to use the cos double angle formula anyway, but that's just the joys of it. So the final integrals I want to talk about are the inverses of the trig functions, like this. The method that we want to use and that you need to know to use is by parts. There's not exactly two functions times together, so we have to use that trick we saw in the by parts video, where we times it by 1, like this. We make u equal to sine to the minus 1 of x. We can't make it v dash, again we can't integrate it. So from the formulas we saw at the start of the video, this will be 1 over 1 minus x squared. Then v dash will be 1 and v will be x. We plug this into the formula and we get x sine to the minus 1 of x minus the integral of x over root 1 minus x squared dx, squidging in there. So in order to finish this one off, we need to know how to integrate this right hand side. That's going to be a substitution with u equals 1 minus x squared. I'm not going to fill in the full details here. Go back to my substitution video to see if you can work it out. And for the inverse of cos and for the inverse of tan, we use exactly the same method. In fact, the substitution for this is going to be exactly the same. The substitution, if you do tan to the minus 1, it's going to be u is equal to 1 plus x squared instead of 1 minus x squared. And the last thing to mention, I promise this will be it, if you have to integrate something that you don't recognize, say for example cosec squared x, you might look in the formula book, it won't be there, it's not in the integral section. Have a check back to the derivative section because it might just be there. In this case it's going to be minus cot of x plus c. You may notice I've not integrated tan x or cot x yet. That will have to be saved for my next video on integral tricks where I show the ln rule. Well, there you have it, another integration method complete. Thanks for getting tricky with me. Try out this question if you want to test yourself, and as always, don't forget, plus C.